Single rotor system. Here we will study the torsional vibration of a single rotor system. Torsion refers to the angular vibration, that is, when the body is subjected to twist along its axis. This is a major concern for rotational bodies, and it is found in transmission line. The transmission line consists of various equipments like, say, shafts, couplings, drives like gear drive, belt torque, chain drive, and in shafts it consists of crankshaft, propeller shaft, etc. So the reason for torsional vibration is, first is the power imbalance of the engine, second, speed variation of engine, damage of gearbox component, damage of propeller shaft, firing order of multi-cylinder engine, and many more. The theory says that the equation of frequency is given by 1 by 2 pi root Cj by Li. Here C is the modulus of rigidity of the shaft, J is the polar moment of inertia, L is the length of shaft, and I is the mass moment of inertia of disc, or say the rotor. We'll go to the experiment setup and we'll measure the time period for 10 oscillations. So this is the setup for torsional vibration of single rotor system, double rotor system. In two cases, one is without damping and the second is with damping. So you can see here there are two rotors and they are fixed by a common shaft. This shaft is made up of spring steel and its diameter is of 3 mm. This two rotor system can be used for two experiments. One is vibration of two rotor system and another is single rotor system. So in case of single rotor system, we have to clamp it from here. So these two rotors would behave like individual systems. And this apparatus over here, you can see that is for damped torsional vibration of single rotor system. So presently, we'll be doing single rotor system. This is a shaft made up of spring steel and the diameter of shaft is 3 mm. The rotor diameter is 0.19 meter and its weight is 2.15 kgs. So we'll be giving torsional vibration like this and we'll try to record the time taken for 10 oscillations. We'll take 3 such readings and then we'll change the length of the shaft. So presently the length of shaft is this much, which we can measure. So it has to be measured from collet to collet because it is being clamped from here. So this end to that, and it is 50 centimeters. So that is 0.5 meter. When you unclamp this collet, this will behave like a double rotor system. So taking reading for 10 oscillations. 7, 8, 9, 10. So this amounts to 5.68. Once more. So this was 6.57. And one more reading. And this was 6.22. So we can take a mean of these two readings. Okay, one more thing. We can increase the weight of this rotor, so that would be another variable for us. So we'll be using the same masses which we used earlier, and we can clamp it here. So now again there is one more question for you guys. Presently we are using two masses of same value, so these two masses are same, and we are attaching it at the same length, that is same length from the center of the disc. Now if we add more variables, like say we have two different masses on the at the same length, or two same masses at two different lengths, so that is one is here and the other is clamped over here, so what would be the result in that case? That is something which you guys can mention in comments. That would be your takeaway. So this was 9.36. Let's try it once more. This was 9.97. Okay, human error. You see, that's the human error. Once more. So this was 9.93. So now we need to change the length. In order to change the length, we'll have to use some spanners. And yes, if you guys were here, you would have done this. So this will loosen the rod, so the grip, and now if you see, both the rotors will rotate. See, this is rotating freely, it is not oscillating now. You see? So yeah, now it's a two rotor system. Now we can again change the length. We'll increase it by 10 mm only. So 0.60. So this is 0.60. Set. So yeah, this is 0.60. First we'll tighten this one, else there will be error in the readings. So yes, now it's working. So now we'll take another set of readings. So that is, the length is 0.60 and the weight is already added. So to start with, it already died. Okay, so you need to give one more try. Once more. Okay, so this is because the clamping was not proper. You see? It's because the clamping was improper. So now with proper clamping, I guess it should work. Lying out. It's again lying out. So yeah, this thing is normal, so it's fine because our apparatus, like there are certain limitations of our apparatus. Yeah, finally it got there, 9.69. We give one more try. This was grossly different, it was 10.52. You see, that is what is called as human error. This was 10.30. So once more, we can take one more reading for this and we will be done. And this was 10.26. So we have to discard the first reading, 9.69, because these three are of same order. The last one, that is 10.52, 10.30 and 10.26. So yeah, similarly what we can do is, we can again remove this plate, unload this rotor and continue the oscillation, the readings for the rotor at 2.15 kgs and the length of suspension is 0.60 meters. So we'll take all such readings and then we'll compare the results. So we have performed the experiment for two different weights and two different lengths. You can see that in the table of observations. Note that the initial weight of rotor was 2.15 kgs and the extra weight that was added was 125 grams per unit. So grossly that is 250 grams when added. You can plug in all the values in the equation and calculate the theoretical value of frequency and compare it with the ones obtained practically. Now there is difference between the theoretical and actual values obtained. This is because certain parameters play a role in this. You can consider shaft stiffness. It plays a good role because actually this equation is derived for undamped free vibration. But here shaft stiffness causes the damping. Again, shaft straightness, it also affects. Here the shaft was not perfectly straight. Again, shaft length, it is one of the components which play a role, because if we had more length of shaft, we could have got better results. And the last one, which is the main, it is the human error, because it always plays a major role in measurement of the readings. So that's how we can determine the frequency for single rotor system.